Hello. I think we are live. Excellent. Okay. Let me. I do what? Yeah. Major shout out to our massive crowd. This is a crowd size unlike any physics review session ever. I think we're breaking all sorts of records. I'm really excited. We have a whopping 3 people here today. 3. So we'll go at whatever pace you all want, and anyone watching at home can go at your pace too. Except they get to pause it, so that doesn't really count. But I know. Yes. So welcome to the Test 5 review session. I'm your tour guide, Mr. Martin. Come along with me for this journey of circuitry and other things. So probably the first, first you need to be able to understand what exactly everything does conceptually. Today we went over all those sample problems, and those were actually from last year's test, which I've also posted on Canvas. So the entirety of the test plus all the solutions you can find there. Additionally, I've posted this PowerPoint that I'm going through now also on Canvas. So you can hop there and just look at the text if listening to my beautiful, calming voice is not what you're in the mood for right now. I can't imagine why, though. The conceptual bits, a lot of times you find in the multiple choice sections, and a lot of times that's what proves to be a source of great difficulty for people. So the main basics that you need to know are what is current in the first place? What is resistance? What is voltage? So current is just the amount of charge per second passing through any stretch of wire. So if you know how much current is running for a certain amount of time, then you can tell me how many coulombs of charge have passed by. Kind of like current in a river, you can define that in a bunch of different ways, but one way that would work for any case would be how many water molecules passed by a certain spot in this river at any given time. Similarly, current is how many coulombs of charge pass by. They're all carried by electrons, so each electron carries that elementary charge amount, that 1.6 times 10 to the negative 19 coulombs. So rather than counting electrons per second, because that would be, every current value would be insanely huge, we're counting coulombs per second, which makes it the numbers a little bit more manageable. The base unit of current is the ampere, which is just denoted by the letter A, brought to you by the letter A. And it is, it's just a coulomb per second. Now, a lot of times we're dealing with, let's say, big resistances in the kiloohms. Then you're going to get some smaller currents in the milliamps. So be aware that all of these are metric units, and they'll all have metric prefixes associated with it. Oh, right, which reminds me. And this is not on the sheet, but I'm going to go ahead and write it right here. Know them. This caused a lot of issues last test, and at this point, you need to know metric prefixes for each and every test and for each and every assignment and for each and everything. So if seeing this symbol confuses you, go back and study it every single day. Learn them, love them, live them. You need to know micro, you need to know milli, you need to know kilo, you need to know mega, you'll need to know nano, you'll need to know all sorts of metric prefixes. So yes, get those down. You can hop onto, I think, honestly, if you go onto Canvas and just look at the test 1 review, that has all sorts of metric prefixes there. So if you need to review that, go ahead and look at that. It has the metric staircase. It has just the values of all the prefixes. It has all sorts of things. Or go ahead and just Google metric prefixes, because you know what? Google's going to have them all, and you'll get more than I'm actually going to ask you for. But that's important. Literally in any science you ever go into, which some of you are not going to major in science, but you're still probably going to have to take some in college, you need to know metric prefixes. If you've avoided it thus far, congratulations, but you need to know them. Here, I'll even decorate it to make it more enticing. Ooh, here, I'll even highlight it, because, oh, wow, that's not a highlighter. I'll even, I just crossed it out. That's not helping anything. Here, you need to know your metric prefixes. Now it's highlighted. Here, I'll put little, I'll put little golden stars all around it, because you really need to know your metric prefixes. So learn those. All right. So any of these metric prefixes can go with any of these units, be able to convert back and forth. So you'll need to know that resistance, the purpose of resistance is to slow the flow of current. So on any given path, whichever path has the highest resistance, it gets the least amount of current. Whichever path has the least amount of resistance gets the most current. And that can be measured in ohms or kiloohms or milliohms or microohms or nanoohms. I've never heard of nanoohms before in my life, but I guess it's possible. And voltage is the energy per coulomb of charge. So a lot of times I think of voltage as quite literally potential energy. And when you drop voltage over the resistor, you're dropping to a lower energy value. Yeah. So those are the main basic things that you need to know. From there, we hop into some equations, starting with Ohm's law. V equals IR. If you don't have this memorized by this point, you have been literally sleeping through every single class, because this comes up all the time. It can be applied to the entire circuit, which basically tells me that V total is going to equal I total times your equivalent resistance. It can be applied to a single resistor. So that would be the voltage drop over resistor 1 is equal to the current going through resistor 1 times the resistance of resistor 1. And it can be applied to a simplified group of resistors within a circuit. What that means is, let's say I've got a circuit where I have, here's a fun reminder, metric prefixes. So let's say I'm looking at a circuit with, let's say I've got a resistor here, and that's 2 ohms, and I've got a resistor here, and that's 3 ohms, and then I've got two resistors on this leg. I've got a 1 ohm and a 2 ohm. I can absolutely simplify the far right resistors down to become, let's see, 2 ohms, 3 ohms, and then add up the 1 and 2, and you get 3. So I can use V equals IR on this fake 3 ohm resistor if I want to. And that can help me figure out the current down that leg, for example. If I know how much voltage I'm dropping in total down that leg, I can figure out the total current down that leg, which I can then apply to the 1 and 2 ohm resistor up there. So that's what I mean by a simplified group of resistors. If you break down a series or break down a parallel bit, then you can still V equals IR that broken down bit, or that ghost resistor, like I sometimes call them in class. So don't be afraid to do that. You all good? We've got 1 thumb up. We've got 2 thumbs up. And 1 hold up. Oh, now I've got a thumbs up. Okay, we're moving on. Voltage rule. Oh, well, the Kirchhoff's rules in general. First and foremost, this is voltage rule, which just tells me that through the course of one path around the circuit, the total voltage gained equals the total voltage dropped. So if you've got multiple paths that you can possibly take, it'll be the sum of the drops over those resistors should equal the voltage gain from the battery. Total voltage gained equals total voltage drop. And that's going to be path by path. Sometimes you may end up with circuits where this will let me do what I wanted. There we go. Where you'll have a battery, R1 here, then R2 here, then R3 here, R4 here, and so on. So in this case, I could use this path, I'll highlight in green. That'll take me from R1 to R2 and back to the battery, or I can go over this purple path, R1, R3, R4, and back. So what that tells me is that I'll label this with epsilon. Epsilon stands for the EMF of the battery, which is just the battery's voltage. So that tells me that the EMF is going to be equal to the voltage on resistor 1 plus the voltage on resistor 2. It'll also tell me that the EMF is equal to the voltage on resistor 1 plus the voltage on resistor 3 plus the voltage on resistor 4. This right here is the purple path, and the other one is my green path. So make sure that you're able to figure out path by path the total voltage drop. This is great for not only figuring it out as you go through to solve it, but for going back and double checking yourself. At the very end, once I've analyzed my circuit, I really need to go back and just with my finger draw a loop of the circuit and add up all the voltage drops for each resistor that I come across with my finger as I do that. And if they do not add back up to the battery's voltage, I have done something wrong. I need to go back and correct it. The nice thing about circuit analysis is if you give yourself enough time, you can go back and do these checks, and you can figure out before you hand in the test whether you're right or wrong. So that's good. That's good. The trick, if you're wrong, is troubleshooting it and figuring out where you went wrong. Then there's the good old junction rule. And that tells me that the total current entering the junction equals the total current leaving the junction. Once again, this is really, really helpful for not only figuring out the circuit in the first place, but also for going back and double checking yourself. So if I get a circuit here, and let's say here's R1, and then I get to a junction and it splits this way. Here's R2, here's R3, here's R4. Whoa, my resistors are going crazy. And let's say I know that there are 2 amps of current coming out this way. And then I figure out from Ohm's law and other parts of circuit analysis that 1.5 amps are heading down this way. That tells me at this junction right here, which I'll label that junction A, down here is junction B. At junction A, I've got 2 amps incoming, and then I've got 1.5 amps plus additional current exiting. I can immediately tell that there's only 0.5 amps remaining, and that must be the current going down this other branch of the circuit. And that would be the current that hits both of these resistors. Because once I figure out 0.5 amps are leaving junction A, that's the full current all the way around until I get to junction B, where my 0.5 amps and my 1.5 amps meet back up. So at junction B, I've got a total of 1.5 plus 0.5 coming in, and that means 2 amps exiting. And that's, just one example, but just be able to figure out something about your current that way. So that's another test you can do. After you analyze the circuit, head to each junction, look at it, and see if you can tell yourself, based on your calculations, how much current's going into it, how much current's going out of it. And if those numbers don't match up, something went wrong at each and every junction. Aha. And we got different types of circuits, series versus parallel. In a series circuit, the current is the same. It has to be, because quite literally, there is nowhere else for the current to go. You've got to go through one resistor, then through the next resistor, and at no point can the current branch off and go in a different direction. Meanwhile, each voltage drop is not necessarily the same. I can shed 3 volts at one resistor and 6 volts at the next one and 19.5 at the next one. All that matters is that the total voltage, when you add it together, is the same as the voltage from the battery. But they do add in series. Now for a parallel circuit, that's where you've got one R1 here, R2 is off on this side, and then the battery is somehow hooked up to both of them. Now for each parallel leg, the voltage drop has to be the same across each leg. If there are multiple resistors on a single leg, you need to resolve those into one single resistor on that leg before you can go on and treat them in parallel. Once you resolve them into one resistor on each leg, then the voltage drop is the same across each resistor. But the current is not, because the grand total current leaving the battery is going to split. Some of it's going to go one way and some of it's going to go another way, but it'll add back together to your total current at the end when the junctions come back together, or when the various paths come back together at that junction. And that's the same for capacitors as well. For capacitors in series, the amount of charge that each plate builds up is the same, and the amount of voltage that each capacitor stores will add to the total voltage. Versus in parallel, the charge, the total charge on each plate will add to the charge spat out by the battery, and the voltage will be the same stored in each capacitor. So these current and voltage rules persist, whatever, regardless of what type of thing that you put there. You're going to need to know your equivalent resistance rules. So when they're in series, the resistances just add. Nice. This would be for a total series circuit, or if you just zoom into one tiny part of the battery, one tiny part of the circuit where resistors are gathered. If they are in series with one another, you just simply add their resistances and treat it as if there was one resistor on that little leg. An important thing to remember is when resistors are in series and when they are not. So if I've got, let's say, R1 here, I've got R2 here, I've got R3 here, there's no path for the current to go except through all these resistors, so that means they're in series. If I've got, let's say, R1 here, R2 here, but then I've got R3 here, now there's this pesky little junction right in the middle, and it's falling between R1 and R2, and it's falling between R1 and R3. And the total current that comes out of the battery goes through R1, but then it splits. And I'm getting different current values through R3 than I got through R1. And I'm getting different current values through R2 than I got through R1. So because of that, this is not a series circuit. And in fact, none of these resistors that I drew up here are in series with anything right now. R2 and R3 are parallel, so I would have to resolve that parallel branch first, and then it would be in series with R1 there. Speaking of parallel branches, boom. When you've got resistors in parallel, they follow a little bit of a Different rule. 1 over the equivalent resistance will equal 1 over R1 plus 1 over R2 plus 1 over R3 plus however many resistors you've got in parallel. To tell whether or not they are in parallel, you'd have, let's see, a battery. They don't need to physically be parallel to each other. They can be. But if I've got R1 here, R2 here, and let's go crazy and put R3 up here. Whoa, bro. Then what really matters is the path from one junction to another. If on each path I can only go through one resistor from A to B, then all of these resistors are in parallel with each other. So on the green path, I only went through R1. On the yellow path, I only went through R2. And on the purple path, I only went through R3. So as I've drawn it here, this would in fact be a perfect parallel circuit, and I can treat all of these as parallel to each other. One that would not be perfect parallel, here, let me get rid of these, would be this. If I've got R1 here, then I've got R2 here, and R3 here. Ooh, now I've got a path through R1. That's cool. But another path is going to go through R2 and R3. Not R2 or R3, R2 and R3. And the mere fact that that one blue path goes through two resistors means those two resistors are not in parallel with each other. So I can't just say 1 over R1 plus 1 over R2 plus 1 over R3 for this circuit, because R2 and R3 are not in parallel to each other. First, I would have to add R2 plus R3, get one resistor on that leg, and now that one resistor would be in parallel with R1. Question? Yes. Correct. So the question was, if R2 is 2 and R3 is 3, then I would add them together, and 5 would be my resistance for that leg, for that right side leg. That's correct. Yeah. Yes. So then I would resolve the parallel bit as 1 over R1 plus 1 over 5 would equal 1 over the equivalent resistance of that circuit. Yeah, that's perfect. If you keep going from, okay, so what if I had an R4 where you keep going from R2 and then it's in line with 1 and 3? So you're saying like here? No. Where? Here, I'll hand the iPad to you and you can draw it. Here you go. Oh, sorry. Yeah, I should have warned you about that. The pen pops off. Ah, okay. That's a really good question. Yeah. So if you had a new R4 farther on the right, away from 3, that's a really good question. Yeah. The top's right next to you. Thanks. So yeah, if you had that, then I would look at my various paths, and this would have to be broken down bit by bit. So here, let me redraw it a little bit neater for you. So you've got, oh no, just because it's far off to the side. No, your drawing was wonderful. I liked it a lot. I what? You did. Did I do this right? R3 and this isn't right. What did I do here? I had R1. Okay. You know what? Let me just bring this back. Here we go. I'm just going to bring this back, and then I'm going to slide it on over. Done. My green check mark came back for some reason. And I'll label this R4. There we go. Okay. So the way that this is drawn, I'd have a path just through R1 and done. I'd have a path through R2, R3 and done. And then I'd have a path through R2, R4 and done. Crap. So now I can't say that R2 and R3 are in series because there's a junction between them. I can't say that R2 and R3 are in parallel because there's a path that takes me through both of them. So what I would do first is resolve R3 and R4, this parallel bit right here, and break that down into a single resistor. That would then look like this R2, and then you've got one more resistor, and that's your R3/4. Then I would add, right. So for the parallel resolution, I would have to do 1 over R3 plus 1 over R4 equals 1 over, I'll say R3/4. And solve for R3/4. That would be your value for this resistor right here. Then I would take R2 plus whatever the resolution of 3 and 4 came out to be, and that would become the resistor on this far leg. Yeah, because that's in series. And then I would take whatever that value came to and have that in parallel with R1, and then you're all resolved and done. Yeah. So a lot of times this just takes breaking it down tiny bit by tiny bit, 2 or 3 resistors at a time. You all are very good at finding ways to solve big problems with a one calculation setup. But in this case, really, you're going to want to break it down 1, 2, 3 resistors at a time. Slowly take, well, this is in series, break that down. Well, these little bits are in parallel, break that down, and continuously replace it with 1 resistor every time you break it down. And that's it. I'm going to take a quick break to make sure that I'm still actually streaming, because it has failed on me before, and I just want to make sure that it's not failing on me right now. Hey, we are still going. That's nice. Okay. Now we'll go back. All right. Now, typically the best steps for circuit analysis are to find the equivalent resistance, use the equivalent resistance to find the total current using Ohm's law, and then you're going to have to use Ohm's law and the junction and voltage rules to complete a chart like this, where for each resistor you keep track of the voltage drop across it, the current through it, and the resistance. Now, be careful. A lot of times it's tempting to just slap down the total current for all the resistors. The only types of resistors that get the total current are the ones that are directly in line with the battery. Basically, if you leave the battery and there is no junction and you come to a resistor, then yeah, that resistor gets the total current going through it. Or if you've got some final resistor that leads directly into the battery with no junction between it and the battery, then you've got the total current going through it there. Otherwise, you should have values less than the total current in this chart. Same deal with voltage drop. A lot of times it's tempting to just say, ooh, I've got a 20-volt battery. I'm going to throw 20 volts at each of my resistors. And that's only going to work if you've got a perfect parallel circuit. Basically, if there's a path that involves only the battery and that one resistor, then great. That one resistor gets the full voltage. Otherwise, if every single path takes you through 2 or more resistors, then every single resistor in this row is going to have a voltage drop that's smaller than the total. And that's the reason why I suggest that you find the equivalent resistance and total current first, because all the values in your table will be either equal to or smaller than that. If you start getting numbers bigger than your total voltage or bigger than your total current, you've already done something wrong. Just something good to keep in mind. Along those lines, I wouldn't try to just blindly add your voltage drop values across the entire row. You're going to have to go back to your circuit picture and actually draw your paths. Because on one path, maybe I'll encounter R1, R4, and R6. And in that case, I'll go to my chart and just add R1, R4, and R6 voltage drops and hope I get back to the battery. Yeah. And then I just put these back on just to remind you of where this whole thing started. Imagine a pump that brings the water up a certain height. That's the battery. And the height, the more height you have, the more potential energy you have. It's very similar to voltage. So the battery provides voltage. Woohoo! Then you've got the waterfall, which is where, that's like a resistor, and that's where you drop your voltage. So if you've just got a one battery, one resistor circuit, then the total voltage gained equals the total voltage dropped. And that's it. If you've got a series circuit, then my individual voltage drops might be a little bit different. Right here, V2 is bigger than V1. But when my pump brings it back up, then my V1 plus my V2 drop equals the total voltage from the battery, epsilon, or sometimes I write it as V total. Both are the same thing, epsilon and V total. Yeah. And with, but one thing to keep in mind is that the total current running around here, oh, that's pretty. Every single water molecule is going to go over this first waterfall, and it's going to go over this second waterfall. So the current is the same in series. Here, in parallel, the current's not exactly the same. Some of it's going to go down this way. Some of it's going to go down this way. And some of it's going to go down this way. But when you get to the bottom, all the current comes back together into one pool. And all that current is what makes it into the battery that pumps it back up. But notice that in parallel, the total drop is the same no matter which side you go to. So my voltage drop over 1 is the same as my voltage drop over 2, is the same as my voltage drop over 3, is the same as the voltage from the battery. And then you get the weird circuits that have, on one parallel branch, a series of steps. But if I resolve that series and just add them up, then I get my total drop over this side, and it's the same as my total drop over this side. Power of a circuit we talked a lot about I talked a lot about in a video, and you did a few problems with it in homework, and that's about the extent that we got to it. But power is simply current times voltage. So it works for the overall circuit. The total current coming out of the battery times the battery's voltage is the total power output of the circuit. And it works for individual resistors. So once you fill out that chart and you know what the current is through R2 and you know what the voltage drop is over R2, then I can find the power dissipated in R2 as simply current times voltage. Power, just like in the fall semester when we did that powerful as a horse activity, it's measured in watts. Current is measured in amperes, which is just coulombs per second, and voltage is measured in volts, which is simply joules per coulomb. And interestingly enough, if you go through and do a little bit of dimensional analysis on it, you will end up with, let's see, IV, well, that is an amp times a volt. Whoa. And an amp is a coulomb per second, and a volt is a joule per coulomb. So when you multiply those together, you get joules per second. And if you remember from the fall semester, power is just change in energy over time. So a joule per second is simply a watt. What? Okay. No, a volt is not a watt. Joules over seconds is a watt. Yeah. A volt is a joule per coulomb, and a watt is a joule per second. Yeah. So that's just, I mean, I'm probably not going to test you on this stuff, but that's where P equals IV comes from. All right. You've dealt with multimeters over the course of a few different lab activities, plus some in-class activities. You can set your multimeter to measure voltage or current, or a wide variety of other things, resistance, capacitance, inductance, a bunch of other stuff. So an ammeter measures current, a voltmeter measures voltage. An ammeter, well, since the current going through several resistors is the same, you gotta place your ammeter in series so that the current that goes through your meter is the same as the current going through the resistor. And because of that, it needs to have really low resistance, because if it doesn't, it'll dramatically alter the amount of current going through that circuit. And I don't want to change the amount of current just by going in and measuring it. I want it to be the same as if my meter is not there. A voltmeter, meanwhile, you need to place in parallel because resistors in parallel experience the same voltage drop, and I'd like my meter to experience the same voltage drop as the resistor that I'm measuring. It has very high resistance because of that, because I want to draw as little current away from the original circuit as I can. I don't want to severely change the circuit just by putting my voltmeter in place. But a lot of times you can measure both of these things with just one single device. Swanky. And then we moved on to resistivity and did a lab with those resistivity coils. So R is the resistance of the wire. That's measured in ohms. And that's really the whole purpose of measuring resistivity, is to figure out how much resistance you're going to get in wires. This is super important for certain circuits where you need to be very, very precise in how much current you draw to a certain region of it, because the wire itself is going to slow that current down with its resistance. It'll equal its resistivity, and resistivity depends on a few different things. It depends on the material that the wire is made out of, and it depends on the temperature of the wire. So I'll show you exactly how that's broken down in just a bit. L is the length of the wire. That'll be measured in meters. And A is the cross-sectional area. For a wire, which is a cylinder, the cross-sectional area is a circle. So don't forget that the area of a circle is pi r squared. That's something you'll probably need to know as well. Where r is the radius measured in meters. Sometimes I'll give you the diameter in millimeters, actually a lot of times. So don't forget that diameter divided by 2 is also radius. And to convert it all back to meters. Because if I don't then I will get a resistance not in ohms, but in ohm meters squared per millimeter squared. And that doesn't really help a whole lot. Now for this rho value, you'll have a chart where you can pick out the material and it will give you a rho value specifically at 20 degrees Celsius. If it's not at 20 degrees Celsius, you've got an extra step you need to do to find what your rho value actually is. And that's here. So rho naught, once again, is resistivity at 20 degrees Celsius, which is about room temperature. Rho is your actual resistivity, your current resistivity. Current. It's funny because the same word means a different thing. I saw this one thing. I can't even remember what it was. But there was this little kid who told a joke and then was like, if your friends don't understand the joke, explain it to them because then it will be funny. And that's always true. The more you explain jokes, the funnier it gets. And alpha right here is the temperature coefficient. That mess is measured in inverse degrees Celsius, and that also depends on the material. So once again, I will give you a chart with alpha values, or I'll just straight up tell you in the problem, the temperature coefficient for silver is this value. And delta T is going to be the change from 20 degrees Celsius to your actual temperature. Aha. The change from 20 degrees Celsius to your actual temperature. Right. So if my wire is at 100 degrees, then that means my delta T is 80 degrees. And that's what I would actually use in my equation. Cool. Forward. You'll need to know a bit about capacitance, particularly the charge on any given plate. Well, each plate is going to be charged up where one is positive and one is negative, but they both have the same absolute value. Notice here that I labeled this plus Q, I labeled this minus Q, and the equation just involves Q. So let's say Q equals 3 coulombs. That means here I've got plus 3 coulombs, here I've got minus 3 coulombs, and in this equation, I'm plugging in 3. So I'm not plugging in 6 because there are 2 of them. I'm not plugging in 1.5 because there are 2 of them. I'm just taking that absolute value of the charge on one plate, and that's what I'm using as Q in my equation there. That'll be measured in coulombs. Delta V is the change in voltage, or the voltage stored on that capacitor in volts. And C is the capacitance measured in farads. A lot of people ask me what is capacitance, and frankly the answer is just the ratio of charge to voltage difference. A lot of it depends on the spacing of those parallel plates. The farther apart they're spaced, the more charge you need to build up to get a significant change in voltage, and vice versa. And you can calculate the total energy that you're storing in joules as simply 1/2 times the charge times the voltage value. Okie doke. U stands for energy. U is potential energy in joules. Onward. Ah, yes. When you've got a capacitor in a circuit, the moment you close the circuit and allow current to flow, the capacitor basically acts as a wire, because the first little bit of charge approaches that first plate and it repels an equal charge on the opposite plate. So it's almost as if that capacitor wasn't there. But that first charge that approached the first plate is not able to make the jump over that little gap. So it gets stuck on that first plate. Meanwhile, the battery continues to push more and more charge that continues to pile up on that plate. Eventually, the capacitor builds up a voltage that's equal to the battery's voltage that it's hooked up to, at which point it will repel any incoming charge with pretty much the same strength that the battery would be pushing it, and all the charges would stop moving. And now you've got what's essentially a break in the wire. No more current is flowing, and you've just got a charged capacitor and a battery that's not outputting current, just sitting together, not doing a whole heck of a lot. And that's essentially how a capacitor behaves in a circuit. If you then take that charged capacitor and hook it up to another complete circuit that doesn't have a battery in it, well, now the positive and the negative charges have a path to reach equilibrium, and the capacitor will discharge and lose its voltage buildup exponentially, which we'll talk about when I get to the RC circuit slide, which is coming up very shortly. I'm going to take one more break just to make sure that I'm still good. And yes, I am. And let's keep going. When you've got capacitors in a circuit, if they're in series, they've got the same magnitude charge. This is when I pulled people up in front of the classroom, put together a circuit with a bunch of strings, and each person was a plate of a parallel plate capacitor. Basically, all that happens is the charge flows from the battery and piles up on this first plate, causing the second plate of the first capacitor and the first plate of the second capacitor to become polarized. And it continues to happen down the line. So each of these capacitors build up the same amount of charge. Meanwhile, the voltage, they may have different capacitance values. So from Q equals CV, if I've got the same charge but different capacitance values, then I'm going to get different voltage values. So the voltage values are not necessarily the same, just like the voltage drops of resistors in series are not necessarily the same, but they will add up. You can actually take these two ideas of the same charge and additive voltage and end up with the equivalent capacitance equation in series, which just so happens to look a lot like the equivalent resistance for resistors in parallel. Cool. So capacitance in series follows the reciprocal rule. Resistors in series simply add. What is what? Oh, EMF is the voltage from the battery. So EMF is battery voltage, or total voltage. And EMF has that symbol epsilon, or V total. Either, I kind of use them interchangeably. Capacitors in parallel, meanwhile, there's no reason for the charge to be the same across the plates. But just like the current of resistors in parallel all add up, the charge built up on capacitors in parallel also all add up. But the voltage stored in each of them is going to be the same as the battery, the same as the EMF. So you can take these two ideas and find that capacitance in parallel simply just adds up. And our 3 attendees are hard at work jotting things down, so I'm going to take a quick break. Oh, before last test, I told cat stories when this happened. This morning I woke up, and when my alarm goes off, my cat likes to sit on my neck or chest, or and actually for Christmas this year, I bought my wife a stuffed avocado, which she said she absolutely loved, but now the cat has taken from her. And each and every night, the cat is kneading on and drooling on her avocado. So, yeah. Um, so this morning, my cat was kneading on the avocado. My alarm went off, and I was like, all right. I start to get up, and I didn't realize that my cat had cut across behind me. So I elbowed her straight in the face as I got up, but she forgave me quickly, which was good news. That was a good way to wake up. All right. And finally, RC circuits. So resistance times capacitance equals the Greek letter tau, which looks like a fancy squiggly T. And tau is what's known as the time constant. It is measured in seconds. So I should probably clarify, I'm not saying time constant or time constants, as you often see. This S stands for seconds. That's the unit of the time constant. Resistance times capacitance. Then you'll have different equations for whether you are charging or discharging the capacitor. One, the voltage on the capacitor at any given time is VC. When you are charging it, VC starts at 0 and then builds up over time to be the same as the EMF, that epsilon value, or the battery's voltage. When you are discharging a capacitor, that means you have to have started with a fully charged capacitor, or not necessarily fully charged, but start with a charged capacitor. And over time, that voltage will decrease and head towards 0. So charging, you're going from 0 to a full value. Discharging, you're going from a full value to 0. Either way, it's an exponential curve, either exponential growth or decay. Where t is the independent variable of time that will just march forward as time always does at 1 second per second. I say as time always does. It changes if you move really, really fast or get near really, really heavy gravity. Then time starts flowing at different rates. But I'm not going to ask you a question about an RC circuit near a black hole. Maybe. And tau is the time constant, which is resistance times capacitance. So if I ask a question where I say, after one time constant has passed, then I would just say, oh, one time constant has passed. Well, that means t equals tau. Ooh, and that means the part of the equation that involves e to the negative t over tau becomes e to the negative tau over tau. Oh, come on. Which would simplify to e to the negative 1. And again, that's only after one time constant. If two time constants have passed, this would become e to the negative 2 tau over tau, or e to the negative 2. If three time constants have passed, it becomes e to the negative 3, and so on and so forth. Sometimes t and the time constant are not particularly related, in which case you just got to grab the raw values of both of those and slap them in the equation. Cool. And that's all that's going to be on this test. So I know it feels like a bit less of a time than usual between this test and the last one, but there's a whole bunch of stuff we've done in that little bit of time. So again, this document's on there on Canvas. Last year's test is on Canvas. And not only that, there's one other thing that I want to show you. On Canvas. So if you head to Module 9, there's this thing called circuitpractice.swf. This was actually created by one of my students from my first year teaching. It's a Flash-based quiz. The problem is Flash is really on its way out, so it's difficult to get to work. It will not work on mobile devices or tablets. And I think Google Chrome is actually kind of phasing Flash out as well. So if you hop on, I think it should work fine in Firefox or Edge, or I'm going to shiver a little bit as I say this, Microsoft Explorer. I think it should work fine on all those. But it's a little multiple choice quiz. Here's a circuit. What's the current through this one part? And he came up with, I think, 15 questions of those. So that's a good place to go and practice as well. Not only that, the test solutions and review is a great place to go and look for some review stuff. So I think that's it. We're now late for the robotics meeting, so I'm gonna stop this broadcast.